Chapter 23 is about averages. So for a box with zeros and ones, we can look at our sums to look at the count, or we can do percentages. So when we talk about that, that's things that are useful for things like the count or percentage of, say, like females that use shoe. Or you could look at like the number or percentage of Democrats in Utah or something like that. So those would be numbers, things where we look at the counts or percentages. But for some values, we have different kinds of numbers. So like your like the number of females or number of Democrats, things that it's either like yes or no, then you look at the count or the percentages. But other things, you have more like numerical values. So like your height is not two values of just yes or no. Your height can be an infinite number of values. Like you can be 5 feet, you can be 5 feet 1, you can be 5 feet 1 and like 0.2 inches. Or your weight, your age, your test scores, okay, things like that. You're looking at actual specific numbers and not just a yes or no. And in that case, we're going to still look at the sum, but now it's just going to be like the total. So like, what's the total test score for everyone in the class? Or what's the total weight of everyone on the airplane? Something like that. Or we look at the average. So what's the average test score, the average height, etc. Now an average, theoretically, is just a rescaling of the sum. So for example, 237, 100 draws are going to be made with replacement from a specific box. Now, number one, if the sum of those draws is 7,611, what was their average? Well, how do you go from a total to an average? Or how do you even find an average? An average is just equal to, you add them all up, so the sum, and then you divide by how many there are, which would be the number of draws. Right? That's the formula we've always done for average. You add them all up and divide by how many there are. So in our specific case, the sum is 7,611. There were 100 draws, and so my average is 761.1. So that would be my average. You can also go backwards if you want to. So like number two, if the average of the draws is 73.94, what is their sum? You could just change that equation around, multiply both sides by the number of draws, so the sum is the average times the number of draws. Now these aren't formulas we memorize or really are even going to use that much. This is just a little bit of background. So the average is 73.94, times it by the number of draws of 100, and we get, oh, sorry, I didn't divide correctly either. The average should be 76.11, and the sum should be 7,394. And so once again, sums and averages, they're very much related. They're just scaled, just rescaled. Now, Chapter 3 has two main parts. First, we're going to look from the population to the sample. So if we know what's in the population, we can do a little bit of theory to see what we would expect in our sample. And then we're going to do the opposite of, if we know what's in our sample, what can we expect in our population? But this video, we're just going to look at what happens if we go from the population to the sample. So remember, a couple formulas. The expected value of a sum is the number of draws times the average of the box, and the standard error of the sum is the square root of the number of draws times the standard deviation of the box. So for example, 238, we want to fill in our table for draws made at random from the box. I say the table because that's going to be on the next page. So here's our box. We have the tickets 0, 2, 3, 4, and 6. The average of the box is 3. The standard deviation of the box is 2. I just did this in my calculator. On your homework and on the test, I'll also just give it to you. It will be written like this. So number one, now let's say we want to draw from this box 25 times with replacement. So A, let's find the expected value of the sum. So expected value of the sum Once again, I put the formulas up above. So the expected value of the sum is the number of draws times the average of the box. So this is going to be 25 draws times the average of the box, which is 3. So that gives me 75. And find the standard error of the sum. That's the square root of your number of draws times the standard deviation of the box. So the square root of 25 draws times the standard deviation of 2, that should give me 10. Now let's just remind ourselves, since it's been a little while, what does this mean? Where's this means? We expect the sum of 25 draws to be about 75, give or take 10. So that's what the expected value and standard error tell us for the sum. But now we might not be interested in just the sum, we might be interested in the average. And really, in real life, the average is used much more often than the sum. It's just more common, we just use it more. So for C, let's now convert those expected values and standard errors for the sums to the averages. So how do you change from a sum to an average? Remember we wrote up above that an average is equal to a sum divided by the number of draws. So the expected value for the average should just be my old expected value divided by the number of draws. So my old expected value was 75. The number of draws is 25. So that's going to give me 3. Oh, I need to convert both of them. And the standard error for the average is going to be the same thing. Just take your old standard error for the sum and divide by the number of draws. So the standard error for the sum was 10 divided by your number of draws, which is 25, and this gives me 0.4. So what does this truly mean for us? So we would expect our average to be about 3, give or take about 0.4. So we can do the exact same thing that we've been doing for the average, or for the sums, but now we just change it to averages since that's actually used more in practice. So let's continue our example. So once again, we have the average of the box is 3, the standard deviation of the box is 2. Now let's see what happens if we draw 100 times. So the expected value of the sum is equal to the number of draws times the average of the box. So this is going to be 100 times 3, which gives me 300. And the standard error for the sum is equal to the square root of your number of draws times the standard deviation of the box. So the square root of 100 times the standard deviation, which is 2, gives me 20. So we expect the sum of 100 draws to be about 300, give or take 20. Now for C, let's convert the expected value and standard error for the sum back to averages. So the expected value of the average is just going to be your old expected value of 300, and just divide by how many times you drew of 100, and you get back to 3. And the standard error for the sum is your for your average is your old standard error of 20 divided by how many times you drew, which gives me 0.2. So we expect the average to be about 3, give or take 2. So we've done that for 2 different numbers of draws, for 25 draws or 100 draws. So I filled in this table for the different number of draws. And we're going to see if we notice any patterns. So we have 25 draws, 100, 400, 900. Then I have the expected value for the sum and average, and then expected value for the sum, expected value for the average, and then standard error for the sum and standard error for the average. So as the number of draws increases, the expected value of the sum gets bigger because you're adding more and more values, so your number should get bigger and bigger. So we went to like 75, 300, 1200, 1800. But the expected value of the average was 3, 3, 3, and 3. Very interesting. So the expected value for the average is the same as the average for the box. And so I could skip the entire formula and skip doing all of that and just say, oh, the expected value for the average, that's just going to be the same as the average for my box, and skip 2 steps. Now the standard error for the sum, that was getting bigger and bigger because as you add on more and more values, you're giving yourself more and more chances for that chance error to kind of accumulate. But the standard error for the average actually ends up getting smaller and smaller. And it's just one of those interesting things that happens. But what it ends up meaning for us eventually is that because the standard error gets smaller and smaller for the larger draws, what that means is that your sample size will give you more and more accurate answers. So the standard error for the average gets smaller and smaller for more draws. And what this means for us is that bigger sample sizes gives more accurate results. So what are the formulas for the expected value and standard error? So we use these formulas where we found the expected value and standard error of the sum, and then we divide by the number of draws. In practice, we're never going to really do that again because it just takes longer. Unless you already know the expected value and standard error for the sum, and then sure, you can use those formulas. But in this, for most of what we do, we're just going to use these shortcut formulas. So the expected value of the average is just equal to your population average. And the standard error for the average is just equal to the population standard deviation over the square root of the sample size. Now that's in terms of real life. For our box models, you could say the expected value of the average is just equal to your box average. Or, that's not what we write it. It's just equal to the average of the box. And the standard error for your average is just equal to the standard deviation of the box divided by the square root of your number of draws. So once again, words like population, average and population, estimating the sample size, that's in terms of real life problems. And the average of the box, standard deviation of the box, it's the correlation to when we use the box models to try and visualize what we're doing. So let's try an example. Haynes women, 18 to 24, have an average height of 64.3 inches with a standard deviation of 2.6 inches. So notice when you read this problem, it's not talking about a box, it's talking about real life things. And so that's why this is my population average equals 64.3, and the standard deviation is 2.6. So my population standard deviation equals 2.6. Suppose we take a random sample of 100 of these women. So my sample size equals 100. What is the expected value of the average height of the women in the sample? And what is its standard error? So we want the average height. That's what we're interested in. So once again, we have our population average, population standard deviation, and sample size. You can, if you want, change it to average and standard deviation in the box instead of saying population average and population standard deviation, because your box is just the same thing as your population. So now let's just use our shortcut formulas. It actually makes our problems very simple. So the expected value of the average is equal to your population average over, no, it's just equal to your population average, which is 64.3. And the standard error of your average is equal to your population standard deviation over the square root of your sample size. So my population standard deviation was 2.6, and the square root of your sample size, square root of 100, gives me 0.26. And you've done all the calculations. That really wasn't too bad. So what does this mean? We expect the sample average height of 100 women to be about 64.3 inches, give or take 0.26 inches. So once again, because I know in advance what the entire population is, what I'm interested in is if I took a sample, what would the average be? And because of chance error, every different sample gives you a slightly different average. But I can tell you in advance that I don't know exactly what the sample average will be, but I expect it to be about 64.3 inches, give or take 0.26 inches. So we expect the sample average to be about 100, to be about 64.3, give or take about 0.26. So now, just like we did with sums and percentages, now we get to look at the normal curve for averages. So for a large number of draws, the average of the draws will follow the normal curve with an average of the expected value average and a standard deviation SE average, which means that 68% of the time the average of your draws will be within the expected value of the average plus or minus the standard error, and 95% of the time it will be within the expected value plus or minus 2 standard errors. So the exact same thing we've done with the sum and percentage, now we're just doing it with the averages. And we can use the normal curve to find the chance that the average is within a specific region of interest. So z is equal to our average of interest minus the expected value over the standard error. Just make sure, because we're interested in averages, that we use the average and the expected value and standard error for the average. So a few notes: it doesn't matter what's in the box, because the histograms for the tickets in the box don't actually have to follow the normal curve, because the average of the draws will follow the normal curve, even if the tickets in the boxes are just like zeros and ones. It can be anything you want. The average will always follow the normal curve if you have a large number of draws. So in fact, we don't even need to know what's in the box, we just need to know the average and standard deviation of the box. And how many draws do you need? For averages, the rule of thumb is for it to be a large enough sample size, you need at least 30 draws. And the central limit theorem says as the number of draws increases, so as you have more and more draws, the probability histogram for the average of the draws gets closer and closer to the normal curve. Or we're going to write it like this. So no matter what the individual values in the population look like, if the sample size is large enough, the average, inside this word, the possible averages will be normally distributed, because there's lots of different possible averages you could get based on which sample. And so all the possible averages will be normally distributed, no matter what the individual values in the population look like. So let's write ourselves another note. So remember, if the sample size is large enough, the sums, the percentages, and averages will be normally distributed. Now those are the only things that's true. You can't say that about anything else. But it is true for sums, percentages, and averages, that as long as your sample size is large enough, the sums, percentages, and averages will be normally distributed. Now let's try an example. In 240, our Haynes women 18 to 24 have our average height of 64.3, standard deviation 2.6. Their heights are normally distributed. Suppose we take a random sample of 100 of these women. So from example 239, the last one we did, we found the expected value of the average is 64.3 and the standard error is 0.26. So number one, what's the chance that the sample average will be more than 64.5? Let's just write ourselves a note that the sample size equaled 100. So number one, what's the chance that the sample average will be more than 64.5? So we're looking for a chance. So we know that we're going to want to use the normal curve, and we're going to have to standardize. So z is equal to your average minus the expected value of the average divided by the standard error of the average. So the average we're interested in is 64.5 minus our expected value of the average, which is 64.3, and the standard error of the average, which was 0.26. So this gives me 0.7692. So I draw my pretty picture. Here's Z. And which direction do I want to shade? We're looking for the chance that the sample average is more than. So that means we want to shade to the right. So I pull up my normal table, and I'm looking for a z value of 0.7692. The closest is this 0.75, so the closest is z equals 0.75. So that area to the left, remember my normal curve always gives me area to the left, the area to the left is 77.34. So how do I find the area to the right? I can use the complement rule. So I'll do 100% minus 77.34%, which gives me 22.66%. And what does this mean for us? So this means that, first of all, if you look back at the expected value and standard error, we expect the average of our sample to be about 64.3 inches, give or take 0.26 inches. Now, of course, due to chance error, it's not going to be exactly that. And so we went on and we found a very specific chance. And so like even more specifically, the chance that the sample average is more than 64.5 inches is 22.66%. So first you find the average and how much you expect to be off by, and then if you want, you can go and find specific chances. And so we found the chance that the sample average is more than 64.5. It's about a 22% chance. Now, just as a little note, what's the difference between the standard deviation and the standard error? We talked about this before, but just kind of one more way to think about it. So the standard deviation tells us how far data values are from the average 4 typical data points. So once again, how far are your data points from the average? The standard error for the average says how far the sample averages are from the population average for typical samples. So once again, the standard deviation is how far are your data values from the average. The standard error for the average says how far your sample averages are from your population average. And just as a little note, all of the formulas in this chapter are for simple random samples only. Now, example 241, for a certain gas station, the average amount of gas sold is 9.84 gallons, with a standard deviation of 3.92 gallons. And if we take a simple random sample of 200 purchases from this gas station, okay, now let's stop here and write down what we know. So the average amount of gas sold is 9.84. Now that's for the entire population for everything at this gas station. So this would be my population average of 9.84. And the standard deviation for everything at this gas station, so the population standard deviation, is 3.92. And we're taking a simple round sample of 200, so my sample size equals 200. Now let's go on. Number 1, we expect the sample average to be about what, give or take what. So we want to find the expected value and standard error of this for this average. The expected value of the average is just equal to your population average or your box average, depending on how you want to think about it, which is 9.84. So we expect the sample average to be about 9.84. Now for the give or take, let's find the standard error. The standard error is equal to your population standard deviation over the square root of the sample size. The population standard deviation is 3.92. The sample size is 200. So 3.92 divided by the square root of 200 is 2.77. Sorry, 0.277. So we expect the sample average to be about 9.84, give or take 0.277. Number 2, what is the chance? I know I'm going to want to use the normal curve and I'm going to have to standardize. The chance that the average amount of gas for these 200 purchases is more than 10 gallons. So to standardize, we have our formula for z. Z is equal to the average minus the expected value for the average divided by the standard error for the average. Now my average here that I'm interested in is 10 minus the expected value, which was 9.84, divided by the standard error, which was 0.277. So 10 minus 9.84 divided by 0.277 gives me 0.577. Now we're looking for the chance that this average is more than 10 gallons. So we're going to draw our z equals 0.577, and we're looking for the area to the right because we're looking for more than. Let's pull up our normal table. Looks like our closest to z equals 0.577 would be this z equals 0.60, which has an area to the left of 72.57. So the area to the right, we're going to do 100 minus that, which gives me 27.43%. So my final answer is, so if I take a sample of 200 purchases, there is a 27.43% chance that the average is more than 10 gallons.